I'll start the 11th week of this course, and in the last 2 weeks of this course, the 11th and 12th weeks, I will change topics and I'll start talking about a topic that is extremely relevant for solids, and this is the theory of electronic structure of solids, which is also known as the band theory of solids. So, I'll try to give the basic picture of the band theory of solids, okay, and how it is used to describe the electronic structure of a crystal, okay. And so obviously this will involve some mathematics. In particular, it will involve quantum mechanics, but the level of quantum mechanics that will be required is quite low. So you will require just basics of particle in a box and maybe free particle, and a little bit of qualitative theory of bonding. Okay. So that's about the level of quantum mechanics that I would expect you to know. Okay. So if at any time during these lectures you feel that you don't understand the quantum mechanics, then you should go back and read the basic quantum mechanics of these topics. Okay. And obviously these are going to be short lectures, and they are going to be I'm going to get at the crux of the band theory of solids. I mean, band theory of solids is a very detailed and a very vast topic, okay, but I'll just look at a few basic features of band theory of solids. Okay. So we'll start this in the first lecture with free electron models, okay, and this is the first step. This is a step actually prior to the construction of bands, okay, but it's useful to learn this topic, and it will also give you a refresher of your basic quantum mechanics. Okay. So week 11, lecture 1 will be free electron models. So let's write the wave function of a free particle, and I'll start with one dimensional free particle. Okay, so just to remind you, if you have just one particle in one dimensions, okay, then you can write the Schrodinger equation for this particle as minus h cross square by 2m d square by dx square, and there is a wave function which is a function of x. X is a one dimensional coordinate. This should be some energy times the wave function of x. So this is the basic Schrodinger equation, and you can see that up to constants it is just saying that d square psi by dx square is a constant times psi. Okay. The solution of this is what is called a travelling wave. So psi of x, if you solve this differential equation, you will get psi of x equal to e to the, I will write it as I k x, okay, or psi of x equal to e to the, and I should put a normalization constant. So I will just say I will put a constant of proportionality before this, a e to the minus I k x, where k is equal to square root of 2 m e by h cross square. Okay. So you should be able to verify this. You should be able to substitute this wave function in this differential equation, and you should be able to see that it satisfies it, and it is fairly easy to see. Okay. So what do these two wave functions represent? Okay. To find out what the first, let me call this the first wave function and this the second wave function. Okay. So I'll denote it by psi 1 and psi 2. Okay. So now if you take psi 1 of x and you calculate the momentum. So how do you calculate the momentum? You operate by the momentum operator. So if you calculate the momentum of the particle in state 1, okay, so the momentum operator is minus I h cross d by dx. Okay, and if I operate this on the wave function on a e to the I k x, what I will get is so I have minus I h cross and then I have I k e to the I k x. So, let me write it out explicitly, I h cross d by dx. Oh, I do not want to write the d by dx. So, if I take the derivative, I will get a e to the I k x multiplied by I k. Okay. And I into minus I is I square is minus 1. So, minus I square is plus 1. So, you just get h cross k, and what you are left with is the same wave function that you started with, which is psi 1 of x. Okay. That means this h cross k is the eigenvalue of momentum. So, the momentum of particle in state 1 equal to h cross k. Okay. So, basically k, the k that we use in the wave function, okay, is such that h cross k is the momentum. Okay. What about the energy? The energy, so we have k is equal to 2 m e by h cross square, okay, implies E is equal to h cross square k square by 2 m. Okay. So, the energy of the particle is h cross square k square by 2 m, and since it is a free particle, there is no quantization. What we mean is that k can take any value, okay, and energy can take any value. Okay. Now, in state 2, the momentum of particle in state 2 will be minus h cross k, minus h cross k. The energy will be the same. Okay. And so this state 1 and state 2 are the state 1 represents a free particle with momentum h cross k. So, it is travelling in the forward in the positive x direction. State 2 represents a free particle with momentum minus h cross k. So, it is travelling in the negative x direction. Okay. So, this is the free particle wave function in one dimension. You can extend this to 3 dimensions, and we have already seen this. Okay. I will come to that before I talk about confined particle wave functions. So, in 3D, so the free particle in 3D okay, satisfies psi. Now, it is a function of x, y, z or r. So, r is basically x, y, z. This is a e to the I, k is a vector and r is a vector. Okay. If you want to write in more expanded form, you can write psi of x, y, z is equal to a times e to the I, and you can write k x times x plus k y times y plus k z times z, where momentum, okay, so the momentum is a vector. So, P is a vector momentum, and that is equal to h cross k vector, which can also be written as h cross k x I plus k y j plus k z k hat. Okay. I j k are the unit vectors in the x y z direction. Okay. The energy of this particle is just h cross square. Now, you have k vector square, okay, that is same as k dot k divided by 2 m. So, I can also write this as h cross square. So, k square is k dot k, I can write it as k x square plus k y square plus k z square divided by 2 m. Okay, so, this is a free particle wave function in 3D, okay, and this is the energy, and again the particle is moving with this momentum. Okay. So, now momentum has components, and again there is no restriction on kx, ky and kz. Okay. So, now let us go to a confined particle. So, confined particle. So, let us say the particle is confined particle in 1D, okay, between x equal to 0 and x equal to L. You should have done this problem in your basic quantum mechanics. This is a particle in a box, okay, in a box from 0 to L. So, the wave function psi of x, okay, now this wave function can be normalized, and the normalization constant is root 2 by L sine, and now there is quantization. So, there is nx pi x by L. Okay. So, this has energy equal to nx square pi square h cross square by nx square pi square by L square into h cross square by 2 m. Okay, I am deliberately writing it in this form. Okay, you might also see it in the form nx square h square by 8 m L square. You might also have seen it in that form. This but it is equivalent. I am writing it in this way just to emphasize that this is your kx. Okay, so what it says is that your kx is quantized by L, and nx equal to 1, 2, 3. So, kx can take only distinct values. So, and since the kx can take only distinct values, the energy can also take only distinct values. Okay. So, this is a confined particle in 1D. Okay. If you have a confined particle in 3D, okay, with between with box size being Lx, Ly and Lz. Okay. So, a 3D box with sides Lx, Ly and Lz, okay, will be represented by a wave function psi of x that just looks like a product of the 3 wave functions. So, root 2 by Lx sine nx pi x by L times root 2 by Ly sine ny pi y by L and root 2 by Lz sine nz pi z by Lz. Okay, so, that is a wave function, and the energy is given by, so I will write it by h cross square by 2 m, okay, and then you have pi square by L square times n x square plus n y square plus n z square. Okay, and each of n x, n y, n z can be n x, n y, n z. Each of them can take values 1, 2, 3, etc. Okay, and now all this should be familiar to you, and if you are not familiar, as I said, you can go back to your basics of quantum mechanics and look at the particle in a one dimensional box and particle in a three dimensional box. So, these are exactly these functions. Okay. So, now so what is the basic idea of band theory of solids? Okay. The idea here is to describe the valence electrons in a metal. Okay. And the general physical picture that we have is the following, that if I take a piece of metal, okay, this is a crystal of the metal and there are several atoms. So, let us say there are several atoms ordered in some array. So, I am just showing some schematic picture where there are several atoms, and each atom I am showing in blue. Okay. Now the basic idea here is that in a metal, in a typical metal, each of these atoms, okay, some of the valence electrons of the metal, okay, will actually leave the parent atom and it will freely move in the crystal. So, I am just showing these valence electrons. So, let us say there is a valence electron on the first atom, on this blue atom. So, it actually leaves the atom and it moves freely around in the crystal. So, it moves around in the crystal, and this will be true of all the valence electrons in all the atoms, and so you will have all these valence electrons that are just roaming around, okay, and they come from different atoms. And so, the idea is that these valence electrons are not tied to any one atom, and they are going to freely go around in the metal, and this is what gives the metal lots of its properties like conductivity, etc. Okay. So, the valence electrons of the metal, okay, they roam around throughout the solid, okay. And if you take this piece of metal as having dimensions Lx, Ly, and let me, I will just briefly show the third dimension, it is Lz, okay. Then the basic idea is you can think of valence electrons as free electrons, and I am using the term free in a slightly different context here. So, here the context free means it is not interacting with anything, okay. So, they can move around freely, okay, free electrons in a box, in a 3D box, okay. In the 3D box has dimensions Lx, Ly, and Lz. Okay. So, you can think of valence electrons in a metal in this way, okay, and this is what gives you what is called the free electron model, okay. And what it will say is that your wave function for the valence electrons will have this free electron form, okay. Now, so psi of so now the idea is that there are lot of valence electrons in the crystal, okay. So, several valence electrons, so so if we assume that the electrons do not interact with each other, so assuming electrons do not interact with each other, okay, then we can use the free particle solution, okay. So, the free particle solution, let me write here. So, so we can use free particle solution for each electron. Each electron independently. Okay. So this is the idea of this is one of the ideas of the free electron model. Okay. And so what happens here? So if you use this, then for each electron I can write a wave function that just depends on the coordinates of the electron. Okay. And that will look like the following form. So it will look like 2 by Lx, 2 by Ly, 2 by Lz. Okay, I am just taking all these at the beginning, and you will have sine nx pi x by L, sine ny pi y by L. Okay, exactly the expression that we had before, sine nz pi z by L. So this is what the wave function will look like, and the energy of the electron. Okay, I'll denote it by energy. This is by epsilon. This is energy of the electron when it is in state nx, ny, nz. I'm using the term. I'm using the notation epsilon because this is one electron. Okay, and there are several electrons in the system. So for one electron, this energy will look like h cross square by 2 m, and then k square will look like pi square by L square times nx square plus ny. Oh, that's not correct. Okay, so pi square nx square by Lx square, ny square by Ly square plus nz square by Lz square. And I think I have to make this correction in the previous slide also. So, I will just go back and make this correction in the previous slide. So, this should be nx square by Lx square plus ny square by Ly square plus nz square by Lz square. Okay. Sorry about that. So, this is going to be the energy per electron. Okay. Now, there is something else about electrons. Okay. So, electrons are fermions. So, are fermions, okay, and fermions satisfy the Fermi-Dirac statistics, but basically, so each energy level can have at the most 2 electrons. Okay, so this is one important restriction, and this will turn out to be important when we actually analyze the free electron model. Okay, so the picture is that you have such energy levels, okay, for each of the electrons, and each level can have at the most 2 electrons. So what happens here? So if you look at the energy level, okay, so I'll just plot it here. So I'll put energy on this axis, epsilon nx. I'll just call it epsilon. This is the energy. Now the lowest possible value is when nx equal to ny equal to nz equal to 1, okay, and in this case you have and let me take for convenience take Lx equal to Ly equal to Lz equal to L. Okay, so I'll just take this for convenience, okay, just for this particular case. And so when nx equal to ny equal to nz equal to 1, okay, then the energy will be equal to 3 h cross square by 3 h cross square pi square by 2 m L square. Okay, so that is the energy. Okay. Now, the next possible value of energy is when 1 of n x, n y and L z is 2. Okay. And now, you can have 3 different possibilities. Okay. I will just write them as 2 1 1. So, n x is 2, n y is 1, n z is 1, or you can have 1 2 1, or you can have 1 1 2. And now, the energy is equal to 6 times h cross square pi square by 2 m L square. Okay. Then similarly you can take the next level, which will be 2 2 1 2 1 2 and 1 2 2. So I can write this as 2 2 1 2 1 2 1 2 2, and now the energy is equal to 9 h cross square I square by 2 m L square. Okay. Notice that there are 3 states that have equal value of energy, okay, for this. Okay. So this state is triply degenerate. Okay. The next one I'll just show one more. Okay. So this is 2 2 2, okay, and the energy is 12 h cross square pi square by 2 m L square. Okay. Now, what I want to say is that each of the electrons will have such a distribution of energy. Each of the electrons will have these energy levels. Okay. Now because these electrons are fermions, in each level there can be at the most 2 electrons. Okay. And so if you take all the valence electrons of the metal, then you keep filling them. Okay, you keep filling them. Okay, you keep filling till you exhaust all the valence electrons. Okay, and you keep filling till how many? Okay, let's say you had a case where you had 12 valence electrons. Okay, so if there are only 12 valence electrons, this will be the configuration of this will be the electronic configuration. So the 12 electrons will be in these 12 states. Okay, and what you notice is that this is the highest occupied energy level. Okay. Now, you can I mean here I took a case where you had only 12 electrons, but now you can extend this concept to saying that if you have a large number of electrons. So if you have a piece of crystal, okay, which has nx which has n atoms, okay, then there will be a total of n times the valence electrons. Okay. And if you have a piece of a crystal, okay, that is finite size, then this could be a very large number. Okay. So n could be number of atoms, could be billions of atoms. Okay. So the number of so the total number of electrons that we are looking at is of the order of billions. Okay. So 10 raised to 9 electrons. Okay. And now, so if you look at this diagram, you have to keep extending this free electron picture all the way to 10 raised to all the way, so that you can fill as many as 10 raised to 9 electrons. Okay. Well, if you go ahead and do that, okay, then what you will get is that you will have this energy, okay, and you will have several states, okay, and all you will have several states, okay, you will have a very large number of states, and what you will find is that when you fill all the electrons, then a certain number of them will be filled, okay, and the last energy level that is filled, this is called the Fermi energy. Okay. This is called the Fermi energy. Now, I'll just I mean it is rather important to distinguish this from the, this is not equal to Fermi level. Strictly this is not equal to, okay, except at t equal to 0. So except at t equal to 0 Kelvin, okay, and we will see this as we go along, okay, but the point is that the Fermi energy is defined in terms of the energy levels, okay, and so at t equal to 0 Kelvin, okay, this will be the at t equal to 0 Kelvin, you will start filling the energy levels from the bottom, okay, and you will only fill the lowest energy levels. At higher temperatures, you could have some higher levels also filled up, okay, and you could have some lower levels being empty, but at t equal to 0, you will only fill up starting from the lowest energy level, okay, and so the energy level, the highest energy level that is filled is called the Fermi energy. Okay. And this is a concept that we will be using a lot. It is denoted by the symbol EF. Okay, this is the Fermi energy. Okay. And we will see that for a free electron model, since EF is related to the wave vector k, okay, since for a free electron model you have EF, E is related to k. So we have E is h cross square k square by 2 m. Okay, now we are talking about electrons, so it will be mass of the electron. Okay, then the Fermi energy has a wave vector corresponding to the Fermi energy, that is called kF, that is called the Fermi wave vector. Fermi wave vector. Okay. So these are two concepts that we will be using a lot, okay, and we will be considering the case where we don't have this free electron model. Okay. So now let me conclude this lecture by saying what are the limitations of the free electron model. Okay. So first thing is electrons see a lattice. Okay, so electrons are not just free. Okay, they actually see a lattice. Okay, so lattice has I would say I mean atoms. Okay, and since we removed the electrons, actually they are positive ions. Okay, since we removed the valence electrons from these atoms, so what will be left is actually positive ions. Okay. And so what this picture of the metal will look like is the following. So if you look at valence electrons, okay, now the valence electrons, okay, so even if the valence electrons were allowed to roam around in the crystal, okay, they would see a lattice of positive charges. So what the valence electrons, even if they are allowed to go around within the crystal, they won't just be able to freely move, they will keep seeing the lattice. Okay. So, they are just not able, they are not completely free, as in they cannot just run from one end to the other. They will experience, they will see this periodic lattice. Okay. And so, that is the first thing. The second thing, second and third points are, the second point is slightly more subtle, is that electrons are correlated, okay, and they interact. That means, since all the valence electrons are moving around this crystal, they will see each other. So, one electron will see the other electron. Okay. So, it's not just moving freely, it will encounter the other electrons. So, it will see the other electrons, and it might and that might affect its motion. Okay. And so, so this picture has to be modified to take electron interactions and electron ion interactions. Okay. So, these are some of the limitations. Okay. Now, also you should keep in mind that electrons satisfy something called a Fermi-Dirac statistical distribution. Dirac distribution at temperature T. Okay. So, what that means is that the distribution of electrons in different levels follows this Fermi-Dirac distribution, and we will see this in more detail. Okay. Now, what we will do first is to take the effect of this periodic lattice. Okay. So, electrons should see a lattice. So, the electrons should experience some forces which are periodic. Okay. So, the next topic that we will be doing in the next lecture is to look at electrons in a periodic potential. Okay. This periodic potential is due to the lattice of ions. Okay, due to lattice of ions. Okay, and at this point, a couple of things I want to say. I am not going to make a distinction between lattice and crystal. I am just going to talk about lattices. Okay, so you can think of them as a single atom basis. Okay, so I am just going to talk about lattices because that will be sufficient to give the basic concepts. The other thing is, in this course, so once we see electrons moving in the lattice, we will automatically see the emergence of bands. Okay. So, I will not really be talking about correlated and interacting electrons. Okay. In the next lecture, we will talk about how electrons move in a periodic potential, and we will see how just even if you have electrons that do not interact with each other, even if you have electrons that are freely moving throughout the crystal, okay, but so long as they experience these lattice of ions, you will see that they will naturally form bands. Okay. So, that will be in the next lecture. Thank you.